So let's pick this back up. So try to break the transitions for A to the N, B to the N down into groups. Taking this idea, this logical idea. So to refresh, we have A to the N, B to the N on the tape. And we want to replace an A with an X, saying we've seen an A, and then transition to the right until we see our first B. When we see that first B, we're going to replace it with a Y that pairs the A we turned into an X with a B that we're turning into a Y. Then we'll move back left until we find an X. Move right, hopefully that's an A. If that's an A, we're going to turn it into an X and move back to the right. If we move until we see an X, move right, and it's not an A, then we have a couple things to verify. If it's a B, if the thing to the right is a B, we would want to reject. If it is a Y, then we want to make sure there are no Bs, because we have no A paired right now, so we still might want to accept. So what do the actual transitions look like? I can also go back and show what some of the transitions are supposed to look like. So here was an example of transitions for the last example that we did. So as input, we're taking a tuple, state, whatever we're going to see on the tape, and the output is a triple. The new state will be right to the tape and the direction that we move. How is that process going? How do we feel about writing those transitions? Is it going well?
There's a lot of them.
Yes, there are quite a few of them.
But I think I have like the idea of what they all should be.
Sure. So maybe we move on and look at them. So we're going to have groups with labels with these three main categories. Group for converting an A into an X and moving right until we see a B and converting it into a Y. One group returning to the leftmost A, one group for verification and termination when we get into a state that we don't expect from 1 or 2 if we're still parsing the string. Remember that we don't need transitions for the failure states. We only need to make sure, what does it look like when we know we've run out of A's or when we know we've run out of B's? Are we ready to take a look at the answer? All right, so group 1, converting an A into an X, moving right until we see a B and converting it into a Y. So Q0 is going to be this initial state where we read our first A and we convert it into an X. No other time are we going to be doing that from this very initial state. So we get into Q1, and Q1 is going to be now moving right until we see a B, converting it into a Y. Group 2 was returning to the leftmost A. So here are 3 transitions for that. I guess we should explain each one of these. And from Q1, if we see an A, then we want to do a no-op on the tape. We're replacing the A with an A and just moving past all of the A's. If we see a Y, this is a previous B that has been converted into a Y, which is fine. We again want to do a no-op, move right, skip over them. When we see our first B, we want to move into state Q2, that is this returning to the leftmost A set of instructions. So we found a B, we paired the A we turned into an X with a B that we're turning into a Y, and we're going to start moving now back left to find that leftmost A. How do we find that leftmost A? Now note that we're in a different state where we know that that is what we are trying to do. So we stay in Q2 until we reach that point. So back over all of the Y's, we're going to go left. Back over all of the A's, we're going to go left until we hit an X. We know that X exists because we had to start in Q0, turning an A into an X. That is where we begin. So it is not necessary for us to consider what happens if there is not an X. To be in state in state Q2, we had to have turned an A into an X in state Q0 when the program began. So there will be an X for us to go find. As we see that X, we're going to do a no-op on it, move back right, and switch back to Q0. That turns that next A into an X back at the very top. So now you can see that between group 1 and group 2, as long as the string is exactly A to the N, B to the N, we have some rules now to parse that. But we need a way to terminate now. We need a way to verify that once we are at one of these states and we see something that is different, that we actually have A to the N, B to the N. So we only need 3 more instructions for this. From Q0, if we see a Y instead of an A, that would be one of the concerns where now we want to actually validate, or we've reached the end of the A's. If we've reached the end of the A's, then we need to go validate that there are no more B's at the end of the string. And that's the only way we can come up with an accepting A to the N, B to the N, right? If there's something that we don't expect in any of these other cases up here, then we just reject. Because this has to be true as we go from A to B to A to B to A to B. But here, once we've seen the last A, we just need to ensure there are no more B's. We were going to do that. What triggers it is in Q0, instead of seeing an A, we see a Y. That was the first converted B. So that transitions us to state Q3. We do a no-op and we start moving right. We're going to now move right across all of the Y's. And if this was A to the N, B to the N, after the Y's, we'll see a blank. If it was not A to the N, B to the N, there are more B's at the end of it, then we will run into something that's not a blank, which isn't defined here, so we will halt and reject. The only way we would accept it is if these transitions are true. Where these are the only transitions you need, if this is the form of the string. Any questions on this set of transitions? You would think that it might be more complicated than that, but we really only needed 10. So let's run through this. This machine with those 10 transitions is past AABB. One question that might show up on a homework or exam is to write a sequence of instantaneous descriptions of the Turing machine as it parses that input. So remember that instantaneous descriptions give you everything that is on the tape, as well as the state that you're in right before the place the read-write head is pointing. So go ahead and see if you can write some instantaneous descriptions and then use that turnstile symbol to go from instantaneous description to instantaneous description based on the transitions that are happening. So I'll leave this up as you go try to remember the string is AABB. Then we'll write out those instantaneous descriptions. I will go through this process as well. That is useful. In fact, we can even number these. Let's say we have rule number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It can help you when you write instantaneous descriptions to put that number above the turnstile symbol that says this is the transition that we went through to get from one instantaneous description to the next. So what is the instantaneous description of the very first that we would write before we start?
Q0 AABB.
So we would have Q0 A B B. Saying we're in state Q0, the read-write head is pointed at the first A. Here is everything that is left. Great. So as we go through the turnstile, what rule are we applying to get to the next state?
The first one.
Rule 1. So you can just kind of write a 1 above this as an applying rule 1. Q0 on an A says we're going to get to Q1, we write an X, and we move right. So what is the next instantaneous description?
That's Q1 ABB.
Yeah, X, Q1, A, B, B. By doing this, we replaced this A with an X. We moved right, and we moved from Q0 to Q1. So all of that is embedded in this information. So that's the instantaneous description. Let's go ahead and continue this process of that's a very long turnstile. What rule gets applied next, and how do we finish this off? That next. Back left. People got to the next one. Applying rule 4, we go from state Q1 to Q2. We moved left and we replaced the B that we were pointing at here with a Y. Now the read-write head is pointed at this A. We're in state Q2. Q2 pointed at an A, just moves left. So we're going to apply rule 6. Q2 pointed at an X, rule 7. Q2 moving left. We see an X, we're gonna move right, go back to Q0. 7. Sorry, Q2 we're pointing at Y. This is 5. Am I on board with what everyone else has so far? Any changes? As far as I can tell, this is right. Now we're going back to 0. That case now. All right, so here's my solution. There were 10 transitions in order to accept this. You can see that even for a simple string like AABB, that took a while. That took an annoying amount of time to fully come up with. But that's a Turing machine for you. This is what's happening at the instruction level underneath the hood of a programming language, which is why it's nice that our computers can do billions of calculations per second, because they're much faster at it than I am. Yeah.
So for languages that the Turing machine were designed for, would it be, I mean, maybe not simpler than this example, but generally simpler? Because it looks like what we did here was just simulate a push-down automaton with the Turing machine.
Yeah.
So in general, would solving the problems that it was designed for be more efficient than solving by context-free languages with it?
Not really. We'll see some languages where the Turing machine really shines is in some sets of languages where we don't know if the program is going to terminate, or we can answer a definitive one way or the other. Like, yes, if the answer is yes, but if the answer is no, we'll never know that the answer is no. It can answer questions like that in a way that a push-down automata could not. But if you want an all-purpose machine, one that's capable of taking in as input any program, you wouldn't want to use an NPDA for that, because there are some things that the NPDA can't calculate. The reason we think about and base the architecture of our machines off the concept of a Turing machine is because if it is calculable, the Turing machine can calculate it. Questions on this process? We kind of took a little while with it, but I think that's okay. This seemed like something you can do on a homework or exam. I'm not staring at you, David. I'm checking, checking soon. All right, I think we're good to move on. Once we get into the computability problem, that's my favorite part of this whole class. All right, so hopefully that's what I did. Let's talk about some of the languages that Turing machines operate on. So let's take the Turing machine that we just wrote. Can we recognize a language like A to the n, B to the n, C to the n, such that n is greater than or equal to 1? Rather than writing it all down, maybe it makes more sense to just try to answer the question. Is that possible? Is this a language that a Turing machine can recognize, fully accept or reject, determine if a string is in that form or not?
Yeah.
For really large n, like 10 billion, arbitrarily large n?
Yeah.
The answer is yes. If we recall back to our context-free examples, have we seen this language before? Was it context-free or not context-free? It was not context-free. This is one of the examples that we use for the context-free pumping lemma. So this is not a context-free language. Since this is a beautiful example of a language that an NPDA could not accept, but a Turing machine can, this at least gives us some evidence that Turing machines can accept languages outside of the scope of push-down automata, context-free grammars, anything that is in the context-free language category. What remains to be shown is it a strictly higher language? Is there anything in could you create a context-free grammar that a Turing machine could not accept or reject?
We just simulated the PDA, so probably we just simulate it every other time.
Yeah, that is basically the idea, is you would want to construct a PDA within a Turing machine. If you can do that, then you can simulate anything that a push-down automata could simulate with the Turing machine. So sure enough, this is a class of language that is outside the scope of context-free languages. A Turing machine can recognize anything in that realm, as well as some extra languages, some more languages on top of that. I'm not going to go through this proof, but it's a fun one to go look up and explore. Any algorithm we can write in any programming language can be simulated by a Turing machine. Doesn't matter what the language is. You can write a program in any language, you can simulate it with a Turing machine, which is a wildly fun result. That's something that is just that simple, can simulate all computation. Anything that can be done with that machine. Because we can also write directly to the tape and produce output. We had talked about two different classes of automata in the first couple days of the class. There were acceptors and transducers. Acceptors could just answer yes or no, and transducers could actually produce output. Because we can write to the tape, we can show that Turing machines are capable of producing or determining, given a process, the function of turning the input into the output. So an algorithm transforms input into output. And this is exactly what a Turing machine does as well. It takes the input of what's on the tape, produces output on the tape, and what happens in between is just a function. So the Turing machine becomes a function between the domain of the inputs and the range of the outputs. Very interesting to think about. You write a program and you've really just written a function. Some possible inputs to some possible outputs. So here's another fun example. Let's say that we are going to represent two positive integers, x and y, on the tape as in unary. So what this means is there are a number of ones followed by a 0, let's say, as a separating character, followed by another number of ones. How could you at the end represent x plus y on the tape in unary? What would you have to do? Now, I guess first we have to figure out what we're going to do. Unary is the easiest program. Yes. So X ones followed by a 0, followed by Y ones. What would that program look like?
Would it be just like a simplified version of the binary addition algorithm?
We probably don't even need something that complicated.
I think simplest way would just be replace the 0 in the middle with the 1 and then remove a 1 from somewhere else, like end of the string or whatever.
Yeah,
You have now added the two together.
yeah, you just need a position of shifting the last one or the first some one somewhere to the 0 place.
Yeah.
Interesting. What would that look like? How many transitions do we think that is? And also, are we making any assumptions about what's on the tape? What if there was something we weren't expecting? Yes, as long as it's not within the rules of construction. So if we're just looking for ones and zeros, what if there are two zeros?
It's still outside of the scope of the question, right? It's only for. X,
Depends
Y.
on how you write the transitions. If you're in a state that does something and it's assuming that it is the 1 0 and it happens to be the second 0, you want to have two separate states for that. One state where we're looking for a 0 and one state where we are not. Because then if we find the 0 when we're looking for the 0, that's expected. But if we find the 0 when we're not expecting it, that'll immediately lead to halt and failure because we ran upon a symbol that we weren't looking for. So something like that can help you determine when you're writing a Turing machine program, when are separate states necessary? Whenever you're asking a different question, you may be doing the same thing, skipping over some ones, but now it's important to separate skipping over some ones looking for a 0, skipping over some ones looking for a blank. Those are two separate states. Does that make sense? We want to give it a shot? I think we should write this program. Go ahead and take a few minutes. First of all, take a stab. How many transitions do we think this is?
If we just assume single 0, that would be 3.
I would argue that it might take us more than that to be able to distinguish between. Because you need rules for what do you do on a 1 looking for a 0? What do you do on a 0? What do you do on a 1 when you're not looking for a 0? What do you do on a blank?
Do you do anything different when you're looking for a 0 or not?
We want to reject if we see a 0, if we are not looking for a 0.
Okay, so we're not assuming about input.
Or at least, yeah, you can never assume that the input is valid, but you need to not have a transition that expects that, if that makes sense. If you were to run upon a second 0, you don't want a legal rule assuming that it's the first 0.
So I guess, like, what do we want to do when we see a second 0? Do we want to just reject?
Yeah, you shouldn't have a rule for it, but you should have a separate state. So like a Q1 versus a Q2, one where you're looking for the 0 and has that rule for finding the 0, and another state that does not have that rule for that 0. So if we see that 0, then we know that the input is not in a valid form. We don't have to handle that. We just want to make sure we aren't accidentally calculating a wrong answer for giving an answer for an invalid input. How are we doing? I think we have it. So here is a book example, and I'm not 100% convinced that all of these transitions are necessary. I agree with everything from Q0, everything from Q1, everything from Q2. So from Q0, from where we start, we're just going to skip over all of the ones. We don't care about all of the ones that are in the first number, X. When we see a 0, we're going to write a 1 and switch state. That says now we have seen the transition from X to Y. And by putting that 1 there, we know now that we're carrying a 1 from the end that we need to now go replace. So from Q1, we're going to skip over all of the remaining ones of Y until we reach a blank. When we reach a blank, we're going to move back left and switch to Q2. And here's where I start to get confused by this. Q2 on a 1, we're going to write a 0, which makes sense, but move left. But I guess now we're going back all the way over everything to validate for some reason, but I would argue that we probably don't need to. The Q3 moving all the way back to the left, reading 1s until we see a blank. I guess that validates that there was nothing on the tape before that first 1. I don't know,
There's
there's,
just thinking you should suggest ones before that, like if there's like some 0 before the start.
yeah, I would think that that's something that we would need to do. Is validate that there isn't anything before that. Maybe that's what that's trying to do, but I would argue this doesn't really do that. You could either do that first and say, move left, is it a blank? If it's not a blank, just reject and say invalid input. So you could write it like that. You could take that first 1, turn it into a blank. And then at the very end, once or I guess you turn the 1 into a blank, when you see the 0, turn it into a 1, validate that this ends, and then you have your answer on the tape.
That's what I did.
Yeah, you start by making and that way a single pass from left to right. It is making an assumption that where you start is the first part of the input, but I would argue that that assumption might be okay. Questions on this example or coming up with these kinds of transitions? How do we feel about writing Turing machine programs? Does that feel somewhat intuitive at this point?
Somewhat definitely tedious.
Yes, very
As soon
tedious.
as I lose my train of thought, it's just.
Yeah, it looks like you're looking at assembly code. You're just like, wait, what? You need to comment a Turing machine program to the extent that you need to comment an assembly program. All right, well, this is the end of our introduction to Turing machines, but there's a lot more processing that we will need to do about Turing machines. So let's actually go do that. We're going to talk about some Turing machine models, different ways that we can modify the Turing machine to make it easier to use without changing its computation power. So Turing's thesis says that Turing machines are capable of any computation that a mechanical computer is. How could we try to figure that out? If you're trying to write Turing machine programs for even simple problems, involves a process that is, as we've seen now, tedious and also pretty prone to error. So what would we do to move from describing low-level automata to describing something that is more complicated than that? Or that allows us to represent what a Turing machine can do using syntax and diagrams that allow us to make and show a more complicated program in a way that could break down into something like a Turing machine program.
That is what programming is.
Yeah.
Isn't technically true.
Yeah, that is basically what programming languages are with compilers, is we're going to parse this and make a map between language that is more English-based and language that is more Turing machine-based. So let's start with the assertion that Turing machines are more powerful than push-down automata. Let's move to, we have this definition. Two automata are equivalent if they accept the same language. We can abstract considering classes of automata. So we talked about regular languages. We talked about context-free languages, but there were two different forms of context-free languages. We had the deterministic context-free language and then context-free language. If we have different classes of languages, then we could say that every automaton in the first class, there's an automaton in the second class that accepts the same language, if they're equivalent, and vice versa. We can use this to talk about Turing machines as well. This becomes useful if you want to build a Turing machine that simulates the moves of another Turing machine. This is going to become the basis of a lot of theoretical computer science proofs. Can we construct a Turing machine to simulate the moves of another Turing machine? That way we can use proof by contradiction to say something like, assume a Turing machine program that does this exists. If we show that we can't simulate that on another Turing machine, then we know the construction of that can't happen. Because a Turing machine should be able to simulate anything else that a Turing machine can do. So we can use this idea to also look at equivalences of Turing machines. So what could we add to a Turing machine? What functionality could we add to a Turing machine that would not change the computational class of what the Turing machine can calculate? The first one we will look at is, it's kind of annoying that you have to move left or right after an instruction. What if you just wanted to stay in the same spot? The question I have for you is this class of Turing machine equivalent to a Turing machine that only moves left and right? What do we think? If we were to construct a Turing machine that could move left or right or stay, is that the same class of languages as a Turing machine that can only move left and right?
I think like an example, like where, you know, move right or left or left, right, like can you do that without affecting the input? As if you would, like, you just stay, you know, you don't change that input.
Yeah, you would just have to write an instruction that says, whatever is on a bunch of instructions, whatever we could find in the tape alphabet, whatever is right, regardless of what we see, move back left.
Yeah, I think you could just like do a state, like say, hey, we're just going back and forth, so it would be just the same thing.
Yeah, move right, whatever happens to be there, move left. Right, so we could simulate that on a Turing machine without the stay option. So because we can simulate that, we know they are the same class of languages. There's nothing that a stay can do that a right-left cannot, because we can simulate the stay with right-left. So what this tells us is now we can make a theoretical model of a Turing machine that has that stay, because we can define what it means to stay in a Turing machine that doesn't do it. Now we can make that something that we can do. So in the future, if you would like to write Turing machines that have stay rather than just left and right, you can do that because we have shown that that is equivalent. Does it increase the power of a Turing machine? No. Of course, my walking through this is not a rigorous proof. If you'd like to see that rigorous proof, it's in the textbook. What else can we do to a Turing machine? Are there any other ideas? If I asked you, what do you think you can add? What power can you add to a Turing machine to make it less annoying to use? Or maybe make some problems easier? More than one step at a time, like moving left, left, or right, right, or
Like until you see something about how you do each transition.
okay. Okay. How would you write that as a sequence of transitions or rules within a Turing machine?
Like as far as like simulating that option,
Yeah,
I guess it would just be doing each step one at a time for the simulation part of it.
sure, yeah, but you'd want to have an instruction that says, repeat this rule until one of these other rules applies.
Yeah, so you just like create a state and just say keep going until you hit this and go back to whatever state you would be in if you just.
Okay. All right, so we have some kind of looping mechanism now that says repeat some number of instructions without having to specify each of those instructions. At least in a transition to Turing model. I like it. What else could we do? Think about expanding the model of a Turing machine. What additional components could you add? Could you add additional pieces to it? Let's take a look at some of our options. Taking the tape and adding more tapes. Now the read-write head becomes a multi-read-write head, where there's a position on each of the tapes. So it would look something like this. Do we believe that this has the same computational power of a Turing machine with a single track?
Let this let us go like up, down, left, right.
We have to move the entire read-write head at the same time. So everything moves left or everything moves right
And then
across.
we
all
read
things.
everything at once.
Yes.
Okay.
Yeah, we would have, instead of seeing an A, we would now have states for if track 1 has an A, track 2 has a B, track 3 has a C, then do something.
You'll simulate that like a number coordinator saying these would be the next 3 characters, and then just do that over and over again.
So kind of, yeah. I go back to the unary addition example that we had. If we instead of having X, 0, Y with a bunch of ones and a bunch of ones, now what happens if we have a 2-track system where X is on track 1, Y is on track 2? We don't need the delimiter character anymore. As long as you see a 1 and a 1, then in track 3, write a 2. If you see a 1 and a blank, write 1. Then you could go through and add the 2s and 1s that are at the end, or you'd have other ways of representing the answer on track 3, especially if you start on the right. Then you can start doing the actual binary addition. You see a 1 and a 1, now you know you're writing a 0, going into a state where you're carrying a 1. So you can actually start to represent something like arithmetic moving right to left. But the answer is yes, this has the exact same computational power. And it makes thinking about some types of problems significantly easier. So how about restricting the tape to only be unbounded in a single direction? So now we have a tape that looks like this. The question I have now is not, is this more powerful, but is it less powerful than a Turing machine that is not infinite in both directions?
Like outcome below on the right side, as if we're starting point would be on the left side.
Yeah, so you could, yeah, basically. So it is not less powerful, and this actually harkens to a proof that I will go into. Have we seen this in discrete or in any other class? What is larger, the number of positive integers or the number of integers? What has more numbers in it? You would be wrong. They have the same number. There are different numbers of infinity. And it boils down to, can you have a 1-to-1 mapping of one to the other, such that every number in the second maps to something in the first? And the answer is yes, you can. Because it's infinite, exactly. But it's not necessarily, there are different kinds of infinite. There are kinds of infinite that we can't do that to. And I'll give you an example of that, but let me quickly show you. We'll come to this in some number of lectures. I know we're out of time. If you have to run to a class momentarily, you can get on your way. But the idea is, here we have 1, 2, 3, 4, 5, 6, 7, etc. This continues forever. And on the other, we have all of the integers. So now, how do you map one of these onto the other?
Kind of like the same principle where we said like 8 would be -1, but like further down the line.
Well, no, you would want to map something like this. You'd want to go 1 is 0, 2 is 1, 3 is -1, 4 is 2, 5 is -2, 6 is 3. And this creates a function that allows you to take as input anything, any number on the positive integer and have an associated integer representation of it. The question that I would ask you is there any number in this infinite set that does not have a number in this infinite set? The answer is no. You cannot give me a counterexample of an element of this set that does not have an associated element of this set. And it only works because they're both infinite. As soon as one of these would end, if one of them would end, then we could not do that. But we could create a function that maps one infinite set onto the other, which means that they're the same size. They're the same size of infinity, even though this contains more numbers on this side, and they both go to an infinite length. It's the first really counterintuitive idea that I will throw at you in here. There will be quite a few of them. But this is the same infinite size because such a function can exist. There are other sets where no function can exist. You can't one-to-one map them, which means they are of a different size. I'll leave that to you to consider over until we talk about it in more detail. But that's the reason that this is not where, because it maps directly onto this. This is the positive integers. Going in both directions is the integers. The reason that this isn't any less powerful is because these two sets are the same size. We'll come back to this on Monday. Continue to blow some brains.